Okay, we are now recording. Let's get it set up for the current slide. For some reason. There we go. The system has been really slow. I guess part of it was I didn't use the computer much over the break, so its battery was really low, but it's sort of back to normal now, it looks like. All right, a few announcements before we get going today. This is one I've seen posted around, so you should have seen it, but in case you haven't, this is important. There are informational sessions being held Wednesday, April 4th, that's day after tomorrow, from 11 to 1, and again from 5 to 6:30 on both campuses. On this campus, it's in the faculty staff dining room, okay? They call it a dining hall, but it's just a dining room. From where you are here in this classroom, if you go down this long hallway here until you get to the second stairwell, not to the end of the hallway, just the second stairwell, second exit, take a left, go down half a flight of stairs, and then go wander around the little jig here in the hall, go straight ahead, take a short right, short left, and then you'll see the faculty staff dining room on the left, okay? Just before you get to the cafeteria. You get to the cafeteria, you've gone a little too far. Come back to the room just before that, okay? So that will be Wednesday, 11 to 1, and 5 to 6:30 in the faculty staff dining room on this campus. Now, if you happen to be on the Birmingham campus, it'll be in the Leon Kennedy Center in the cafeteria, which I found interesting because both of those times are meal times, you know. But maybe they'll just have a little corner somewhere off to the side where you can have those informational sessions. Now, what are these informational sessions about? They're about institutional scholarships and summer Pell, okay? Summer Pell, does that sound familiar? Probably not, because we haven't had summer Pell for years, okay? They tried it a few years ago, I'm guessing about 7 or 8 years ago. It worked extraordinarily well. We got lots of enrollment in the summertime because students had more money to come, and then they stopped it after just a couple of years. I don't know why. I heard it politics.
They did it last semester.
Last summer?
Yeah, they did it for me.
Oh, did it?
Yeah.
Okay. I didn't know that. I didn't see that big an increase in things, but they do have that now. But if you don't qualify for Pell, because in the past when they didn't have summer Pell, we set aside money for institutional scholarships to help students maybe only take 1 or 2 classes because we didn't have enough money to keep people full time. But now that we have that money and Pell Grants there, more people may be able to get more money from institution if you don't qualify for Pell. So it's a win-win all the way around. If you want more information about it, go to the information sessions on Wednesday. Okay? I'll leave that up there, but you see them posted all over the place. Math team's still looking for good prime examples of people to be on it. And they're meeting today at 3, every Monday at 3, and every Friday at noon. And the Science Building on the Birmingham West Campus, that's the C Hall in room C100, okay? So go, enjoy, it's a good deal. And we've got tutoring available if you need it, but more importantly, if you can tutor, tutoring is available on both campuses. On this campus, student support services on this hall floor, and almost directly below it, but across the hall from it is the Space Center. On the Birmingham campus, they have the Space Center. And they have some student support services, but I don't know that if students are hired for that. I think it's mostly staff is used for that. But then they also have the STEM lab, and I would think all of you would qualify for the STEM program and consider doing that as well. should have. I kept thinking more people might show up. And I'll apologize ahead of time. I am so tired from my spring break. We were over in Georgia. I grew up on a farm over there, and we have a place there now. And because we got company coming in today and later this coming weekend, so I had to go over and get things cleaned up, yard mowed, that kind of stuff. I worked myself. It was fun. It was outside. It was good, but I'm worn out and stiff and sore. And I did a lot of visiting with brothers and sister and that family, so it was good that way too. But I'm worn out. And last night, I woke up several times just because I was so sore I had to go take something else to be able to sleep. Okay. We started in 3.4 last time, concavity and second derivative test. Any questions from anything we've done so far? First test, second test, what we've done so far in chapter 3. No questions? All right. This is a slide I think we left off on. Oh, goodness, I'm stiff. To find the open intervals on which a graph of a function is concave upward or concave downward, you need to find the intervals on which the first derivative is increasing, that's for concave upward, or decreasing, that's for concave downward. Well, what would tell you when the first derivative is increasing or decreasing? The sign of the first derivative? Yes, that would do it. Well, let's see. How do you tell if a function is increasing or decreasing? Sign of the first derivative. So how can you tell if the first derivative is increasing or decreasing?
Sign of second.
Second, yeah, that's it. You got the first one. The sign was right, but it wasn't the first derivative. It's the second derivative. The sign of the second derivative. So what you do is take the second derivative. For instance, here's a graph. F of x is equal to 1/3 x cubed minus x. There it is. Okay, you have to take their word for it. You can plug in a few values and verify that right. That's right. If x is equal to 0, obviously that's 0. Okay. 0 minus 0 is 0. If x is equal to minus 1, here's Elijah. Goodness gracious, it hurts just to bend over. I mean, everything hurts. Okay. Yeah, that's right. Okay. I was thinking that was that 1, but it's not. Okay. When x is equal to plus 1, this would be 1/3 minus 1, which would be minus 2/3, and there's minus 2/3. When x is equal to minus 1, this will be a negative 1/3. Minus a minus would be plus 1. And that would be plus 2/3. So that looks right. Negative 2, I think, would be a little bit worse. This would be negative 8/3 plus 2 would be 8/3 is 2 2/3, right? So negative 2 2/3 plus 2 would be negative 1/3, and that looks about right. Okay, so yeah, it looks like they got it right. So there's the graph of f of x equal x, 1/3 x cubed minus x. Now, first thing to do is, this course, what's the good? Take a derivative. And when you take a derivative of this, what's f prime? You probably can see it better here. F prime would be
X squared.
X squared.
That's just x squared.
Minus what?
Just x squared.
Okay. No.
Or minus 1.
Minus 1. Minus 1. Okay. X squared minus 1. There it is. Okay. And here is the graph of x squared minus y. Good old parabola, shifted down 1 unit. Yeah, that works. And, oh man, you can look at the places where this is equal to 0. That will give you your maximum or your critical points. And that would be x equal 1 or x equal minus 1, because this factors is x plus 1 times x minus 1. Set it equal to 0, x equal negative 1 or x equal plus 1. And sure enough, there's a maximum there, a minimum there. Your two critical points are local extrema. Okay? Now, I'm not following what they're saying, so let's go back to what they're saying. For instance, the graph of this is concave downward on the open interval negative infinity to 0. Now, and what Clark was saying when he said the sign of it, the sign of the first derivative tells you whether it's increasing or decreasing. Okay? And if it is decreasing, first derivative decreasing, you are concave down. Okay? So that part actually was correct. Okay? But if you look at this from negative infinity, it'd be very large negative numbers to 0. I disagree with this, okay? If you have a very large negative number, let's say 2 is not very large, is it? Negative 2 squared is 4. 4 minus 1 is 3, okay? The first derivative is positive there. I'm sorry. It's positive, but decreasing, okay? Because when you have a very, very large negative number, that's enormous. Because you square a negative number, very large negative number, it becomes positive, subtract 1 from it. It's still a very large negative number. But the closer you get to 0, at 1, this would be 0. At 0, it would be negative 1. It's still decreasing there. But at negative 1, not negative 1, at positive 1, this derivative, the first derivative is 0. Which means, and there it is, that's where you have your minimum for your first derivative. So it quits decreasing there. So what this is saying is your first derivative is decreasing. It is a very, very large positive number here, but becoming less and less positive. So it's decreasing, 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 decreasing until you reach 0. Okay? And at that point, up to 0, then it starts increasing. The first derivative starts increasing again. Okay? So you can say is concave. No, they're saying this wrong. Oh, no, I'm sorry. Yeah, they're saying it right. Okay. The first derivative is decreasing here, which means it's concave down here. Okay? And the first derivative is increasing here, which means it's concave up from this point on. So something happened at 0, didn't it? At 0, it ceased being concave down and went to being concave up. That is the point we're going to talk about next, I believe. Let's make sure. So whether the first derivative is increasing or decreasing, that tells you the concavity. Okay? Now, there's an easier way to do it, and that's the second derivative. I thought that's what they're going to do now, but they're going to wait a while and make you do it this way, and then they'll show you the easier way. Okay, similarly, the graph of f is concave upward on the interval, and this is the graph of f, not f prime, from 0 to infinity, because f prime is increasing on 0 to infinity. It's going upward, okay? The next theorem shows how to use the second derivative, here we come, of a function to determine the intervals on which the graph of f is concave up or concave down. Okay? If this looks a lot like the test for local extrema using the first derivative, yeah, there's a reason for that. Let f be a function whose second derivative exists. If you have something that the second derivative doesn't exist somewhere on an interval, don't even try this. It won't work, okay? But if it does exist on some open interval I, okay? In other words, there's no zeros in the denominator, even in the second derivative on that interval I, you're going to be fine. You know, no places where a square root would be negative. No places where log would be, you're trying to take a log of a negative number or two. As long as none of that happens, that the second derivative does exist on that interval I, if f double prime of x is positive, which means the first derivative is increasing, okay? For all x's in I, the interval I, then the graph of f is concave up. So you don't need to worry about what is the first derivative doing. Go straight to the second derivative. If it's positive, concave up. If it's negative, concave down. That's far easier than determining whether the first derivative is increasing or decreasing. Because this tells you that. If the first derivative is increasing, it's concave up. If it's, the second derivative is positive. If the first derivative is decreasing, even though it may be a positive first derivative, but it's decreasing, then the second derivative is going to be negative. So there is the simple way to do tests for concativity. Concativity. I don't know how you pronounce it. All right. To apply that theorem, locate the x values for which the f double prime is 0, or where the f double prime does not exist. Just like your test for local extrema. Okay, your critical points in first derivative are where the first derivative is 0 or does not exist. And then you look at endpoints too if you have that interval. If you're looking for absolute, or what do they call it? Absolute maximum, absolute minimum. I guess that's what they do call it. Now, but if you're looking for concativity, then you go to where the second derivative of 0 does not exist. Use those x values to determine the test intervals, and finally test the sign of f double prime in each of the test intervals. Just like we did for first derivatives. Okay? Except we found out that now we can do those tests for first derivatives using the second derivative. So here's example 1. Let's do example 1. And this should be on your page 182. Let me get my pen untangled. Determine the open interval on which this graph is concave up and concave down. So what do you reckon we're going to do? Take a derivative, it sounds like right. But actually, before I do that, I would rewrite it, because I don't like having my variable in the denominator. So how might you rewrite that? You can take a derivative without rewriting it, okay? I'll admit that. But I think it's a little easier to rewrite it. How would you rewrite that?
6 times x to the negative.
Say again?
X to the negative 2.
Okay, wait. X squared plus 3 to a negative 1. It's the whole denominator is down there. So you have to put that to the negative 1. Now, you can do it the other way. You can do it using the quotient rule. I just don't particularly like the quotient rule. I have to remember the d high minus high d low, blah, 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 blah. But this, to me, is easier to remember. Okay, so let's take a derivative. F prime of x would then be what? You tell me. Help me, help me.
2x plus
Okay. He's starting off with the derivative of the inside, which would be a 2x. That's good.
And then times 6.
Second,
Times 6.
a minus 6, isn't it? Minus 1 times 6.
Oh, yeah.
Okay.
-2.
Second,
-2. And plus.
not a plus.
Minus.
Nope, just times. X squared plus 3 squared, isn't it? I mean, not squared, to the minus 2. Right?
That's what I was talking about. What I thought it was.
Okay. It's
Oh, yeah.
minus 1 times 6 times this to the minus 1 more. Okay. That's what you were saying, minus 2. You needed that to be the minus 2. Then the chain rule has you times 2x. So starting with the chain rule is fine. That's good. But that's what it turns out to be. Now, is that going to tell you where it's concave up and concave down? It is if you want to pick a bunch of points and see where it's increasing and decreasing. I'm a bit too lazy for that, okay? So what might you do next? Take a second derivative. So f double prime of x would then be what? Well, let's rewrite that one just a little bit just to clean it up some. Negative 12x times x squared plus 3 to the minus 2. Okay. I think that's easier to do than, okay. So let's take the second derivative. Now this time there's a little bit more involved because this is now going to require the product rule. Okay? The first one only required the power rule basically and the chain rule. Huh?
That's what I was trying to do with the product rule on that one.
Yeah, well, yeah, the derivative of 6 is 0, so I did that. Okay, right, okay. This one will require the product rule, so you tell me how to go and I'll go that way, unless I don't like to, okay? So how would you go for this?
-12.
Negative 12 times x squared plus 3 to the minus 2. You took the derivative of the first times the second.
And you say
Plus
-12x.
Negative 12x.
Plus, how many times 2x?
Okay. All right, there's that 2x again. Erase it and then put it right back in.
2x to the
Okay, you did the chain rule part, but you didn't do the power rule part.
-2.
Okay, you still got a negative 2. I'm going to put it out here.
And then x squared plus 3.
X squared plus 3 to the
-3.
-3. Yes, yes, yes. Okay, so let's see what we got now. I'm going to write it now taking out negative exponents because I think it's easier to evaluate there. Okay? So this will be a minus 12 over x squared plus 3 squared. You agree with that? Okay. And the plus, but you have a minus times a minus times a plus. That's just going to be a plus. Now let's multiply all your things together. That's 2 times 2 is 4 times 12 is 48 x squared over x squared plus 3 cubed. All right. So there's your second derivative. in some sort of a formula. Okay? Now, how do you determine the open? Oh my goodness. The open intervals on which the graph of that function is concave up or down. What's the first thing we do? Yeah, set that second derivative equal to 0. Okay? So let's do that. Now, still not quite at the fun point, is it? Because you have two different denominators here. So what do you need to do to make those denominators? And this is an addition of fractional forms, right? So in order to add those fractions, you need common denominator. And what's going to be the common denominator there?
X squared plus 3 to the third.
Yes, that one. So that means we're going to have to multiply this denominator by another x squared plus 3 to make it to the third also. But if we do that, we've got to multiply the numerator times the x squared plus 3. So let's do that. What's that? I still couldn't hear. Yeah, x squared plus 3 up here, and then make this to a third down there. Notice my sleight of hand being really, really, really lazy. Okay, let's see what we've got then. This is going to be negative 12x squared minus 36 plus 48x squared all over x squared plus 3 to the third. And set that equals 0. Okay, you happy with that? Now this, are you? I got to make sure you're happy. I want you happy. Good. Now, how is a fractional form ever equal to 0? Give me a fraction that's equal to 0. Any fraction that's equal to 0.
0 over 1.
Ah, very good. Another one?
0 over 2.
Oh, good. 0 over negative pi thirds, right? 0 over anything. That's the only way that fraction is going to be 0, right? So it doesn't matter what the denominator is. In fact, you don't want the denominator being 0, right? And that denominator, we're not going to worry about it now, but it's x squared plus 3 can't be 0. Well, guess what? It can't be 0, okay? Because x in the real number system, x squared is always positive, add 3 to it, it's always positive, okay? So that's never 0, but we don't even want it to be 0. It's where the numerator is equal to 0. Well, let's simplify that numerator a little bit. What do you get there? Say again? Yeah, well, let's first combine like terms. What you get?
20x squared.
Say it a little louder.
20x squared.
No, it's 12x minus 12x squared plus 48x squared. Right? What does that come to? Second?
60x squared.
No, it's a minus here.
Oh.
And that's a plus.
36.
36x squared minus 36. And we want that equal 0. Now I like your idea of what would you factor out? 36. Yeah, I don't like that much, do I? Okay, and that would be x squared minus 1 equals 0. Okay, you through factoring? No, we can factor some more. 36 times x minus 1 times x plus 1. And that's equal to 0. Okay, now we have a set of 3 factors here. 36 is a factor, x minus 1 is a factor, and x plus 1 is a factor. Now if you want to factor 36 out, you could too. I wouldn't waste the time, because I look at this and say, if this product is equal to 0, at least one of those factors has to be 0. Is 36 ever equal to 0? Never! Not in this universe, okay? So that's not 0. How about this one? Yes, when x is equal to 1. How about this one? x equal -1. So there we have the two places, x equal 1 and or -1. Those are the two places where your second derivative is going to be 0. Okay?
I might be doing this a little bit differently, but would you eliminate the 36 anyway if you saw that?
Yeah, you could divide 3 by 36 and it's out of there. Yeah. So I just didn't want to do that. But both of those are exactly equivalent. Once you have the equation there, you can divide and multiply, but whatever you want to. Don't divide or multiply by 0, ever. Don't do that. Ever. Okay. But 36s you can anytime you want to. So yeah, get rid of the 36. Okay? So that gives you two places where your second derivative is 0. But guess what? That still doesn't tell you the intervals on which they're concave up or down. What do you have to do then? Yeah, plug in something. Okay? Picture your number line here. There's 0, there's 1, there's -1. Okay? These two places split it into this interval from -infinity to -1, this interval from -1 to +1, and that interval from 1 to infinity. Pick a point anywhere in each of those intervals. Plug those into your second derivative and see whether it's positive or negative. Okay? So pick a number left of -1. -2, I like it. Okay? Now, we'll go back to this derivative. Okay. I never did write it as neatly as I could have. I don't do anything very neatly. That'd be 36 times x squared minus 1 over x squared plus 3 cubed. There's your second derivative, right? I just took what we did here, that was our numerator, and put it over at the number. This is the most concise way of doing it. Now let's take a -2. -2 squared, 4 minus 1. 3 times 36 is some pretty good sized number, right? And if we take that same -2 and square it, it's still 4. Plus 3 is 7. Cubed, that's some number, big number. But they're all positive, right? So everything on this side, the second derivative is positive, which means second derivative is positive means concave up. So that's what the arrow up means. Okay? The first arrow is just pointing to which interval, the second one is saying which direction is concave up. Okay, let's pick something in that middle interval between -1 and 1. What could we choose?
0.
Second?
0.
Oh, 0. Goodness gracious. Why choose 0? Okay. Now, if you put a 0 in here, 0 squared is -1 is -1 times 36 is -36. Down here, put a 0 in. Plus 3. Cubed is 27. Okay. But, who cares? What we're interested in is what the sign of that second derivative is. Negative on top, positive on the bottom. So what's the sign?
Negative.
Negative. So what does that tell you about the second derivative here?
Concave down.
Concave down. Okay? And Chasten's here. Talking about being concave up. Okay, never mind. Okay. All right, here's Chasten. Okay. And let's go to the third interval. Pick a point. Second? 2. Why not? Okay, let's look at the second derivative at 2. 2 squared is? -1 is? Times 36 is some big positive number, right? Okay, down here, 2 squared is plus 3. Cubed is some big positive number. And positive divided by positive is? Positive. That tells you that the concavity is up. Okay. So therefore, determine the open intervals on which the graph of this equation, this one here, we haven't done a thing to that except take its first derivative and then later its second derivative. But now we're going to tell you that's concave up on the interval from negative infinity to negative 1, and again from 1 to infinity. It's concave downward on the interval from minus 1 to 1. It's 0 at negative 1 and 1. And then concave up or down everywhere in between. Make sense? So that's all you have to do. Take your, find your second derivative, set it equal to 0. We haven't said what those values are yet. We're going to say it shortly. Okay, I sure hope. I've been wanting to say it all along. I think I probably already have said it all along. And then pick some point in those intervals. That will give you your intervals, your places where the second derivative is 0. And then use a test point in each of the intervals and find out whether the second derivative is positive or negative. Positive is concave up, negative is concave down. Okay? So, let's see what the next slide holds. Ooh, I'm going to have to clear out some writing here. Okay. Begin by observing that f is continuous on the entire real number line. Is that right? Where would be the places it could be discontinuous? In fact, you would almost expect it to be. That would be anywhere where the denominator was 0. That would be a discontinuity, right? Is that denominator ever equal to 0? No. Never on your life. Okay? So therefore, we don't have to worry about, and certainly there's no square roots in there, there's no logarithms in there, so this is continuous everywhere. The first derivative is, the function is continuous everywhere. Okay? Next, find the second derivative. Well, you can't find the second derivative until you find the first derivative. So, and look at this, they rewrote it. Oh, clever idea, wasn't it? Okay? You could have done quotient rule. I think this is a little easier doing just a power rule. And just doing it right, that would be the first derivative being negative 6, x squared plus 3 to the negative 2 power, dropping that by 1, then chain rule, the derivative of the inside would be 2x. All right? Now, I would rewrite that 2 to be negative 12x. I would not put it over x squared plus 3 squared, though that is correct. That's a good way to write it. But then the next thing I would do was go back and write it just like we did before, except having negative 12x times x squared plus 3 to the minus 2. But no, they do a quotient rule. It's okay. It's perfectly all right to use the quotient rule. It works. Just a pain in the neck, okay? Because you have to remember what the little saying is. Low, that's your denominator, okay? D high, which would be negative 12, minus high, D low, and D low here would be 2 times x squared plus 3, 2 times x squared plus 3 times chain rule 2x over that, okay? Over the square, okay? Low, okay? Why they ever did that, I'm not sure, because then they suddenly say, oh, but this is that, okay? Now, if you could see that quickly, yes, go for it. But in reality, you notice what they did here. They saw there is one fact, there's this thing squared up here in this term, and this thing to the first power here, so you can divide out this to the first power, and that leaves you this to, no, they just skip so many steps. It's unbelievable. But that's how they reduced it from the fourth power to the third power. Okay. But then the rest of it, you just have to do it. That'd be minus 12 times x squared plus 3, so that's minus 12x squared minus 36. And then over here, you have to go through and do all this, plus 48x squared is all you've got here. And then you do all that and you get the same thing we get. Okay? I do not see product rule as being easier. I think it's more of a pain in the neck. I would have done it. Kept it in the power rule function and go with that. Just have to do a chain rule on it. But this is correct. There's your second derivative. Then you set that equal to 0 because f double prime is 0 when x is equal plus or minus 1. It's defined on the entire real number line. Again, same reason as before. You have no zeros in the denominator. And you should test f double prime on the intervals from, why they changed the font size, I'm not sure, negative infinity to negative 1, negative 1 to 1, and 1 to infinity. I think because they had to go to a different place to pull up the infinity signs, and that lowered the font. I don't know. It looks bizarre because this one has a small cap and a bottom. This only has a bigger cap with no bottom, and then this is a small cap and a bottom again. The serifs are different, but that's just sloppiness, I think. Okay, so anyway, there's your f double prime. There's your test intervals. Pick points, and they chose, negative 2, 0, and 2. Clever, okay, of them. And we looked at that, and it was the second derivative of negative 2 was positive because the numerator was positive, the denominator positive. The second derivative was positive, concave up. At 0, the numerator was negative, but the denominator was positive. So the whole second derivative is negative, concave down, and at 2, numerator positive, denominator positive. So the second derivative is positive, so it's concave up. And here then is the actual graph of that original function. Okay? It starts here, and in the long run, it's going to 0. Okay? But always concave up here. Okay? Going to 0. And going to 0 here, always concave up. But in the middle here, it reaches a maximum and then goes down again. That means it has to be concave downward somewhere here. These are the two places where your concavity changes. So concave up, second derivative is 0 there, positive here, and then second derivative is negative here, concave down, 0 there, and then becomes positive again. So sine of f double prime, you can determine the concavity of the graph of f. Very good. Any questions on that? It's a lot like we did with first derivatives and extrema, local extrema, okay? Critical points. Now we're doing the same type of thing here with second derivative to determine concavity. Make sense? So the function given in example 1 is continuous on the entire real number line. When there are x values for which the function is not continuous, these values should be used along with the points for which f double prime is 0 or f double prime does not exist to form your test intervals.
Did you go back to that chart?
Go back to what? There?
Yeah. So when x equals 0, how could it be concave down?
Okay. Well, we did it too. Remember, you're not looking at the function, you're looking at the second derivative of the function. Okay? So we go back here, and here's your second derivative, and you put in x equals 0, right? Remember, that becomes negative, that stays positive, negative over positive, negative down. Yeah. Okay. Good question. Excellent question. Okay. Now, I want to say this, and I kind of bite my tongue because I can't say it's always going to be true. But it says when there are x values at which the function is not continuous, okay? If the f value, if the function is not continuous, then I can almost guarantee you the first derivatives are not defined. Well, I can't guarantee it, but they're probably not going to be the same. And the second derivatives, you wouldn't think they would be the same either. So therefore, I would say the second derivative would not exist there. Now, I can't say that's always going to be the case, but I would say most of the time, if the function's not continuous there, the second derivatives are not going to exist there because they'd have to be the same from both sides. And the likelihood of that, I think, is fairly low, okay? But it can exist, and it'll probably exist in the next example we look at. But let's just see. They're skipping example 2, so let's do example 2. All right, let's do example 2 here. Determine the open intervals on which the graph of f of x is equal to x squared plus 1 times over x squared minus 4. Okay? So here is your new function here. This is example 2. F of x is equal to x squared plus 1 over x squared minus 4. Okay. Now, before we begin, if you see a function like this, and we should have really done it on the first one, except it already had stated the function exists everywhere, it's continuous everywhere. It doesn't say that here, so you have to question, is there any place where that function does not exist? Where?
2.
Or?
And
negative 2, exactly. Because when this denominator is 0, the function doesn't exist. And that denominator is 0 plus 2 or minus 2. Okay? So here we say, and I think this is a good idea to do always. You're given a function, look at it, see if there's any place that is x not equal plus or minus 2. Okay? Do that right off the top. Okay? As I just said on the previous thing, that's going to be places that you have to set as boundaries for an interval as well. Now let's proceed and do the rest of it. We're looking for the intervals on which, the open intervals on which this graph is concave up or concave down. So what are we going to have to do? Oh, before we do it though, do you have a preference on what you do with that function?
rewrite it.
How would you rewrite it?
It's x squared plus 1 times x squared minus 4 negative 1.
That's what I would do. That's just because I don't particularly like the the quotient rule. I'd rather do the product rule. However, you could do the quotient rule with that without rewriting. Either way works. Just you choose. Clark likes it this way. Thank you, Clark. Okay, okay. So what's f prime then?
X squared plus 1
X squared plus 1 times 2x times
x squared minus 4 to the negative 2.
x squared minus 4 to the negative 2.
And plus.
That whole thing has to be negative because the negative 1. Yeah, don't forget that. Okay, now you can do your plus.
Plus 2x
2x
times x squared minus 4 to the negative 1.
X squared minus 4 to the negative, what?
1.
1. Okay, I couldn't hear what you said. Okay. Yeah, derivative of the first times the second. Got it. Okay. Now let's I think this will be the best thing to do, just because product rule 3 times is a little bit of a pain in the neck. So let's go on and multiply these two out. See, that's the denominator factor, and these two are numerator factors, right? That's the denominator factor, here's the numerator factor. So I would multiply these together. You don't have to, but I think it just is going to help you in the long run. What would that be then?
2x to the third.
Negative 2x to the third. Say again?
Negative. They're minus 2. Oh, I mean, yeah, it'd be minus.
I would do it that way. Now, you don't have to, but you could leave the minus on the outside and do that, but I just feel a little better getting it in there because I tend to forget about it if I don't. Okay? Times x squared minus 4 to the minus 2 plus, and this will just be, it doesn't change, 2x times x squared minus 4 to the minus 1. Okay? Now let's do your f double prime. And what would that be? Anybody?
Negative 6x squared.
Say that again.
Negative 6.
Okay.
Squared.
Negative 6x squared.
Minus 2.
Minus 2. No. If you do the derivative of the first, just write the second. Product rule, right?
Oh, yeah.
Yeah. So what would that be?
X squared minus 4
To the negative 2. Plus.
So now we're going to need to do the product rule.
Yeah, you're going to do the, yeah, the product rule has 2 pieces each time. Yeah, you do it twice, but it gives you 4 pieces. Okay?
That would be plus, plus 2x to the, oh no, we're doing that now.
Okay.
Negative 4x, right?
Okay, what are you doing now?
And then negative 2, well I did.
You're going to factor it out? Huh?
I got 2x right there.
Right. Oh, you're doing this 2x from chain ruling. Okay, that'll be fine. So we'll do a 2x.
So you'd say times negative 2x to the third
Yep.
minus 2x.
Minus 2x. Got it.
And negative 2x squared minus, plus 8 to the,
Okay, now how did you get that?
because of the negative 2 on the outside.
Negative 2 on the outside times x squared minus 4 on the inside, and that's what you were multiplying through. Yeah, yeah. I want to make sure I understood what you were doing. That's fine. Okay. So you've taken the first term of those 2 terms of your first derivative. Now let's do the second one. And that's going to be a product rule again.
Where we're at.
Second.
Have to figure out where we're at.
Okay. We've done the derivative of this term, product rule. Derivative of this times that plus derivative of this times that. Okay, sort of mixed up there, but we got it. Now we do the derivative of this one. But again, it's a product rule. And what will that give us?
So is that like a plus sign at the end of all that?
Yep. That plus sign right there. We'll just bring it down. I'll do that.
We have 2x.
2x.
We have negative 2x to the
A negative 2x, you said, times what?
times x squared minus 4 to the negative 2.
I think it's x squared minus, did I write it wrong? Yeah, that's supposed to be a 4 there, isn't it? Oh, you didn't catch me on that one. Okay, x squared minus 4 to the
Negative 2.
negative 2. Okay,
And then
plus
x squared minus 4 to the negative 1
x squared minus 4 to the minus 1
2.
times 2. Got it. All right. This is so much fun, isn't it? Okay. I'm beginning to wish I hadn't pulled that factor of negative 2 into that first one. I did it, but I think it would have been a lot cleaner if we'd left it out. But we can still do it. So let's see if we can clean up this a bit. I'm going to do what I just said. I'm going to factor out a negative 2x out of that first term. That'll give us an x squared minus 1. Right? No, plus 1. Okay. Oh, wait. No, it doesn't give us that. I'm looking at the wrong line. Okay. Let's go back. Pulling a negative 2 out. That gives us a 3x squared minus 1, right? And let's go on and put that over x squared minus 4 squared. What's that?
Would it be a plus 1? 3x squared plus 1?
You're right. Plus 1. Okay? And I'm going to pull out a minus because, no, I'm going to pull out a plus. I think. Okay? And here we have a 2x, a minus 2, and a minus 2. So that's going to be a plus 8x. Okay, and then the numerator there, we pulled out a minus 2. We could have pulled out another x. Let's go on and do that. And that's going to leave us a x squared plus 1. Sorry about that. I know. Oh, I've left off a sign here, haven't I? Yuck. I think my mind's still on spring break, okay? When we did, yuck. Yuck. This is a minus 3 here, isn't it? Yeah, it's got to be. Okay. Time out. Okay, let's go back to here. Here is your first derivative, right there. And our derivative of that we did derivative of the first, minus 6x squared minus 2 times this, okay? Plus, and then we did this one times the derivative of this one, which is your minus 2x squared minus 3 to the minus 3. That's what I left out. And then your chain rule had the 2x here. So yeah, that's that term. And then this one was your plus 2x times the minus 1 times 2x, which made it a minus 2x, times this thing to the minus 2. And then the derivative of this one, which is 2, times this one. Okay, there. So I left off the minus 3 there. Now what I'm doing here, I notice this is a factor of 2x, that is 2x. This one you can factor out a minus 2x, so that'll give you a minus 4x squared, but then the minus 2, that'll give you a plus 8x squared. Okay? That covers that. What you're left with here is x squared plus 1, because you factored out the minus here. And this last term was, that's where when I saw my error, is going to be x squared minus 4 to the minus 3. Oh, but I didn't want to write it like that, did I? Okay. Whoa! That's not what I wanted. Okay. This, okay. I wanted to write this over that cubed. Okay. Sorry. I know this can be pretty confusing, right? X squared minus 4 cubed. I just brought that downstairs. See, everything else is numerator material. That's the only part that's denominator. Okay, then we get to this term, that third term there. Can you see that when I do this? Can you see that little? Yeah, you can see that. Okay, there. So let's see what we got. We got a 2x times a minus 2x, so that's going to be a minus 4x squared over x squared minus 4 squared, right? Okay, and this is this one is going to be a plus 2 over x squared minus 4 to the first power. Okay, I sure hope I got it right this time. Okay, there's your second derivative, all written on one line. Okay, but I have no more board space to write on, so I'm going to have to go back up to the top and start doing some erasing. Okay, so can I erase this, and that, hoping we got them right? Okay, let's do that.
Is there a reason that one got so messy, like the way we did it? Or?
No, it's just a messy problem. Yeah, it's their fault, not ours. I don't think. I think the product, the quotient rule would have been just as messy. Okay, I'm hoping so anyway. If not, go back and do the quotient rule. Okay. All right. Now, I want to leave that other part there. We don't need that first derivative really anymore, so I'm going to take that out. Okay, I really don't need the first part of the second derivative, but let's just leave it in there because that's what we're dealing with. Okay. But this is where we got to it last time, is how to get that as a simpler thing. Notice all your denominators are factors of x squared minus 4. This one's to the second down here, third, second, and first. So your common denominator then is going to be x squared minus 4 cubed, right? You agree? Okay. So this first term here is going to be a minus 2 times 3x squared plus 1 times x squared minus 4 to the first power, because you had to multiply that squared by x squared minus 4 to make it a cube, right? Okay. The next one is just the term you have, plus 8x squared times x squared plus 1. I want to go on and let me go on and multiply that through. Is that okay? Okay. So let's just make that plus 8x to the fourth plus 8x squared. You okay with that? All right. Minus 4x squared, and this one we have to multiply by an x squared minus 4, right? Agreed? Because that was over squared, so we had to do that one. And then lastly, we have to multiply numerator and denominator by x squared minus 4 squared. So that would be a plus 2 times x squared minus 4 squared. All right. Now, what are we going to do with the second derivative? Going to set it equal to 0, aren't we? Okay? So we don't care really about this denominator anymore. Except that still, you can't have x equal plus or minus 2. But you couldn't from the beginning, so you still can. But nothing else is that's contributing to as far as our 0. So let's just worry with the numerator. Okay? So, therefore, I'm going to erase the denominator if it's okay. Remember, it's in there. Now, let me erase down below, because I don't want you to forget that it's in there. Okay? So we'll erase this term. This line. Not really a term, a line. Okay. And this one too, that went with it. And hopefully we've simplified it well. Okay. Alright, so I'm just going to deal with the numerator of your second derivative now. Okay. Whew, boy. Let's multiply these two together first. Okay? Wouldn't that be 3x to the fourth minus 12x squared plus x squared minus 4. If I've done all my other parts right, that should be what that gave us. Do you see that? Okay. And then we're going to multiply that by minus 2. So it'll be a minus 6x to the fourth plus 24x squared. Oh, let's do that. Minus 11. So it'll be minus 20. Plus 22. Sorry. X squared. See, I should have gone on and added these two together, making it minus 11x squared times a minus 2 is minus 20. Plus 22x squared. And then we've got a plus 8. Correct? Okay. Second one is a plus 8x to the fourth plus 8x squared. All right. And then we can multiply those together and make it a minus 4. Why am I writing an 8? Minus 4x to the fourth plus 16x squared, right? Now, we got to square this one. Can we do that in our heads? X to the fourth minus 8x squared plus 16. You okay with that? Okay. So multiply 2 by that, and you get plus 2x to the fourth minus 16x squared plus 32. Now we want to combine like terms. Okay. So let's look at all our x to the fourth terms. There's a 8 and a 2 is 10. And here's a, oh my goodness, minus 6 plus 4 is minus 10. Can it be that their x fourths all disappear? Sure looks like it to me. Okay. Well, then let's go to our squared terms. There's 30x squared, And these two add to 0. So that just gives me a 30x squared. And now let's go to the constant terms. Plus 8 plus 32, so that's plus 40. Is that right? Right? Sure looks like it to me, unless I've messed up a sign somewhere. And you set that equal to 0, and you get absolutely no values for which that second derivative is equal to 0, do you? Because x squared is never negative. And add 40 to something that's never negative, and you got something that's always positive. So that's interesting. The second derivative cannot equal 0. So guess what? That has just these values here, which is where your second derivative is not defined as well. That's what I was saying before. Where the function's not defined, that's going to be where the second derivative doesn't exist. And it doesn't exist at those places too. So those are our test points. So what we have to do is get something to the left of minus 2, in between plus and minus 2, and something to the right of plus 2. And those are our test points. Right? Now, I'm going to cheat big time here because I can. Okay? Remember, this was my second derivative here, right? F double prime of x was this thing right here. And what we did on the line below for the numerator, that just came up with that numerator. We simplified that numerator right there. So what I'm going to do, because I can, is erase all of this one, right? Everything there. All our chickens. Oh, I erased too much chicken scratch. Okay. Erase all of that. You don't need to erase it. You just write it down somewhere else. Okay. And replace that with 30x squared plus 40. Right? So now I can erase all that. This thing here, this f double prime numerator thing. I'll erase all these lines that are connecting. And there's the second derivative in its simple form. Did you ever think it was going to come out that simple?
No.
It wasn't looking promising, was it? Okay. All right. What's that?
We can still factor out a 10 from that.
Wait, just, I can't hear you. Say it again.
I was just saying we can still factor out a 10.
Yes, we can. Okay. So let me go and erase this. That'll make life a lot easier. That's what you want to write? Okay. Now, we want our 3 test points. Did you choose them?
-3. 0.
Oh, yeah, I like it. Yeah, okay, let's do f double prime of -3. Okay? Let's use that simple form there. That'd be 10 times. And you know what? I'm not really interested in the number. All I'm interested in is the sign. That numerator is going to be what? Positive. Okay? So rather than working out all this, I'm just going to put positive over, and what's the denominator going to be? Positive. Okay? So that's going to be positive. So guess what we got? For that first interval over here, from -infinity to -2, what are we? Which means? Concave up. Okay. All right. Next interval will be from -2 to 2. Okay, and the value you chose was 0. So f double prime of 0 will be, numerator is? I'm not interested. Yeah, I'm not interested. No, the numerator isn't 0, but it's positive, isn't it?
Oh, yeah.
Yeah, because when x is 0, that'll be 40. So I'm going to write 40 down. How about that denominator, though? Negative, yes. So guess what? On this interval, it's concave down. Okay, let's do to the third interval, which is from 2 to infinity. Okay, and which number you wanted 3 there, didn't you? Okay, f double prime of 3 would be, numerator is going to be positive, denominator is going to be positive. So that's concave up. So there we have it. Your second derivative test gave you no places where your second derivative was 0. Didn't happen, okay? So we just use those places where the function wasn't defined. That determined our intervals. We found out positive on the left, negative in the middle, positive on the right. You can almost picture what it looks like. Can I erase all this now? You've got it written down, right? Okay, so I will erase it all. I don't want to erase it all by hand, so I'm just going to erase it all. And then I'm going to go back and write back in what my function of f of x was equal to x squared plus 1 over x squared minus 4, right? Yeah. Okay. And we know right off the top that we have a vertical asymptote at -2 and a vertical asymptote at +2. Okay. And it's real easy just to look at that and say, what is f of 0, right? What would f of 0 be? -1/4. Yeah. So let's say it's right there, okay? -1/4. So there is 1 point there, okay? Now, we know it's concave down there, right? Okay? Now, there are other ways it could be concave down. No, I don't think there is. Well, I don't know. But this is a really good guess. Okay? Now, why do I say it's a really good guess? Because this is an even function. Right? So whatever it's doing on this side, it's going to do the same thing here. And it's concave down. So that is going to look something like that. Maybe not exactly. Now, another thing that we know is and this is calling from your Math 112, remember that? A long time ago? Okay, your end behavior. This is a rational function. Okay, there's your vertical asymptotes. Your horizontal asymptote is the ratio of the leading terms. And what's that? Ratio of x squared over x squared. 1. So y is equal to 1 is your horizontal asymptote. Okay? So that leaves, and you have to be concave up over here and there. You are going toward the horizontal asymptote. You can't touch that one. It's got to be going like that. Same thing here. Without doing any more test points, you know just by the things and it's symmetric about the y-axis. It's an even function. So it's got to be something like that. Now, the way they drew it in the book, I didn't have a big enough hump here. I probably should have been a little more like that. I had it too sharp of a peak there, but you see it's there. No, really not much doubt about it. And by the way, they wound up in the same form we did. The second derivative was 10 times 3x squared plus 4 over x squared minus 4 cubed. Now, the thing is, in the book, they skip steps like crazy. Okay? They just jump from one form to another form as if you were automatically there. And actually, probably what we could have done on that first derivative, we should have simplified it. You know, made like terms and things like that, and that would have made life easier. So to answer your question, yeah, part of the way we did it was, but we, I still think if we had done that, I've already erased it, but I think if you go back, you can see that was happening. Okay, no places at which the second derivative was 0, but at your discontinuities, there are your intervals. All right, through with that. Let's move on to points of inflection. I've been wanting to say that all along. If the tangent line, goodness gracious, to a graph exists at such a point where the concavity changes, so let's get that again. If the tangent line to the graph, that's first derivative, right, equals 0. Tangent line, well, I'm sorry. Tangent line to the graph, that's any tangent line. It doesn't have to be 0. It doesn't have to be a horizontal. The tangent line to a graph exists at such a point where the concavity changes, then that point is a point of inflection. I've never heard it phrased that way, but it's true, okay? And that point is a point of inflection, okay? 3 types of points of inflections are shown here. Okay? Here we have something like we just had in several examples here. Concave up, then at some point the second derivative was 0 and it's concave down. Sure enough, the tangent line does exist there. Okay? I don't know why they say it that way. Here we had one. This is like a cubic function without any middle terms in it, square terms in it, or even linear terms in it, just a pure cubic function, you know, shifted, you know, stuff. Concave downward here, concave upward here. There is a tangent line. It happens to be horizontal. Okay? That's also an inflection point. There, the first derivative is 0, and the second derivative is 0 at the same point. That would be true there. This one, the first derivative is non-zero. Second derivative is 0 because it's a point of inflection. You know, it changes its concavity there. This one is the weird one. It's concave up here, concave down there. It has a tangent line, except the slope is not defined. It's an infinite tangent line. So sure, there is a tangent line there. So that's the point of inflection. Okay? The tangent line, the slope is not defined there. So I don't know why they said if the tangent line to a graph exists at such a point where the concavity changes, then that point is a point of inflection. Okay? Note that the graph, oh, that's what they meant. The graph crosses the tangent line there. They left out a word here. If the tangent line to the graph exists at such a point where the concavity changes, and they had to mean something else, okay? I think I see what they're saying. If the function crosses the tangent line, then it's a point of inflection. If the tangent line to the graph exists at such a point where the graph crosses that tangent line and the concavity changes, then at that point is a point of inflection. I don't know. I mean, I can't figure out the mind here. What they said up there is certainly true, okay, but what they say down here is where it crosses, the graph crosses the tangent line at the point of inflection, and that's got to be true. So the top parts could have been said a little better, I think. All right, so here's a definition of a point of inflection. Let f be a function that is continuous on an open interval, okay, function continuous on an open interval. Now notice, remember our last one was not. It wasn't continuous on the interval. It was from negative infinity to negative 2, and from negative 2 to 2, and from 2 to 5. It was continuous on those three intervals, but not from negative infinity to infinity. So let f be a function that is continuous on an open interval, and let c be a point in that interval. If the graph of f has a tangent line at the point c, f of c, which if it's a continuous function, I'm going to say if it's continuous, it's got to. It would have to be a smooth continuous function to have it. So it has a tangent line there. Then that point is a point of inflection of the graph of f when the concavity of f changes from upward to downward or downward to upward at that point. I'm certain that's a true statement. I don't know why they make it so complicated. To locate possible points of inflection, this is where we need to be. You can determine the values of x for which f double prime is equal to 0 or f double prime does not exist. We said that before. This is similar to procedure for locating relative extrema of f. So here, rather than here, this is the better one. Points of inflection. If c, f of c is a point of inflection on the graph of f, then either f double prime of c is equal to 0 or f double prime of c does not exist. Why have all this in here and crossing the tangent line and stuff? I don't see any point. This is it. Okay? And I was wondering, why in the world are they bringing all that other stuff up? It's true, I'm sure. That's it. There's your test. And as we said before, if the function didn't exist at f of c, then that's not a point of inflection, but it may be so f double prime either will not exist or is equal to 0. So here we have example 3. Yes, I think we have time to do it. Maybe. Let's see. Now, okay. The little example they give is not an example, but in the verbiage they have at the bottom of page 193, you have a piecewise defined function. Okay? The definition of point of inflection requires that the tangent line exists at a point of inflection. Some calculus texts do not require this. Okay? For example, for instance, after applying the definition above to the function, a piecewise defined function, where the function is pieced together and the left-hand derivative is not the same as the right-hand derivative at that point, x equals 0. And you can see, no, they don't. They didn't even bother to draw it. If you're going to do it, at least show it. Okay, they didn't show it. You will conclude it does not have a point of inflection at the origin, even though the concavity changes from concave downward to concave upward, but the first derivative doesn't exist. And that's because it's a piecewise defined function. I thought that's what they were getting at, but I thought, why even bring this up? Okay. So, to locate possible points of inflection, okay, blah, blah, blah. So, let's move on to example 3. Determine the points of inflection and discuss concavity of the graph of this function. What's the first thing you're going to do? Take a derivative. Sounds like a wiener to me. Okay, and what would that be?
4x third minus 12x squared.
Perfect. Okay? Now, time out. Let's get this straight. Get our thinking right at the very beginning. What kind of function is this? A good old polynomial function. And what do we know about good old polynomial functions? They're smooth and continuous everywhere. So the first derivatives exist everywhere. Their second derivatives are going to exist everywhere, that we need them to anyway. All right, so we don't have to worry about, places where it doesn't exist. This exists everywhere. So move on from there. What's the next thing we would do? Take a second derivative. Take a derivative of the derivative. Okay, and what does that give us?
12x squared minus 24x.
And then what are we going to do with that?
Factor out a
Well,
12x.
you can't until you set it equal to 0. You can't just factor out. I'm sorry. You could have factored out and expressed it differently, but set it equal to 0. Now factoring makes more sense. And what do you factor out?
12x.
12x, and it leaves you with a
X minus 2.
x. What do you say?
Minus 2.
Minus 2. Okay, I can't hear well. That's equal to 0. Now what do you know from that?
Positive 2.
Okay, either x equal positive 2 or
0.
x equals 0. So those are two potential points of inflection. Okay, where the second derivative is equal to 0. There's no place on a polynomial function where the second derivative is not going to exist. So we've got our two candidates here, and let's discuss the concavity at various points there. Do we want to have a test point? Second?
From negative infinity to
Okay, our intervals then would be negative infinity to, what do you say?
0.
To 0, and from
0 to
2, is that what you said?
2.
Okay, and from?
2 to infinity.
Got it. Because polynomial functions defined everywhere. Okay, pick me a test point between negative infinity and 0.
Negative 1.
Okay, how about between 0 and 2?
1.
And between 2 and infinity?
3.
Second?
3.
3. I like it. Okay, so let's go back to our second derivative here. And you can either use the factored form or the other form. I don't care. I kind of like your idea of having in factored form. F double prime of x equal 12x times x minus 2. So let's do f double prime of negative 1. And what would that be? All we're really interested in is the sign.
Negative.
Okay, this will be negative. That'd be a negative 12 times.
Oh, and negative 3.
3, so that would be positive. It happens to be 36 at that point. Whatever, what does that tell you?
It's up.
Concave up there. Okay? How about at 1? F double prime of 1. Okay? Would be negative. Okay? So it's concave up here, concave down here, and then F double prime of 3. Positive, which means
It's concave up.
concave up. So determine the points of inflection. Sure enough, they're at x equal. Okay, now here's another thing, and they haven't said it yet, but I imagine they do. Your points of inflection, you just can't say at x equal 2 or x equals 0. You need to give points. So when x equals 0, what is f of 0? F of 0, not f double prime of 0, f of 0. 0, okay? And f of 2. That would be
32.
second. Would be 16 minus 32. Is that right?
No.
No. F of 2. 2 to the 4th. Huh? which would,
I can't.
okay, 2 to the 4th be 2, 4, 8, 16. And then back up 1 and make it 8. Minus 4 times 8 is 32, negative 32. So that'd be 16 minus 32, which is minus 16. So at x equals 0, so your point of inflection is 0, 0, and 2 negative. I can't write. Okay. 2 negative 16. Okay, those are your 2 points of inflection, and discuss the concavity. It's concave up from blah, blah, blah. Okay, so let me erase this quickly. Hopefully we did it right. If not, we'll just pretend we did. Write the original function. Wow, I got that. Okay, and take a first derivative. We did that. Second derivative, we did that. We even factored it like that. And setting it equal to 0, you got your points of inflection, possible points of inflection at x equals 0 and 2. And we tested the intervals, and we found out that sure enough it was concave upward between anywhere to the left of 0. It was 0 at 0. Plug that in. 2 negative 16. Why they graph like that, I do not know. Why they have 9s? Why didn't they do 8s? That would have been so much better. Negative 8, negative 16. I don't know. Okay. That is about negative 16. And then it's concave up from there on. What we didn't realize that it had a minimum. But we could have gotten that from our first derivative, which we've already erased now. But we could have gotten that first derivative. We would have found a critical point here, but it wouldn't have a relative extremum. This critical point did have a relative extremum. We didn't go back and do our critical point, but if we had, we would have seen that. And this is a point of inflection here and here. It's concave down here and concave up there, so it had to have a point of inflection. So sure enough, we had it. We'll do a little, hopefully they'll do a little bit more on when they do the second derivative test, which, okay. What we'll have to do is start next time at this one. Okay. And we'll pick up and go from there. Sorry, went a little extra over, but guess what? I want no extra charge. Okay. Yeah, you get it for free. What a deal.